welcome to Belgrade, and it's a very nice place to have our conference. And here is our mini symposium. The topics of our mini symposium is the data-driven and deep learning in action, smart monitoring, analysis, and damage prediction for materials and structures. This mini symposium is organized by me, Chao, from Norwegian University of Science and Technology at Norway, and also Professor Chiara Bertolin, also from the NTNU in Norway, and also Professor Chao is from Harbin Institute of Technology in China. So I would give short minutes to introduce about our mini symposiums. So the main topics of our mini symposiums is machine learning and data-driven design for structure and material performance. The second main topic is the condition monitoring and the risk assessment of historical structures. And finally is the integrated approach for predictive maintenance in heritage and modern infrastructure. The time of our mini symposiums, we will have 2 days. Today is from 11 to 1:30, and also tomorrow we will have the same time slot from 11 to 1:30. And the room of our mini symposiums is always this, I think it's the largest rooms, even on the rooms. And approximately each presentations we will have 15 minutes. Roughly speaking is 12 minutes for the presentations and also 3 minutes for the question and sessions. But that if you need more times, that's completely fine. You use the 15 minutes because we can leave the discussions into our coffee break. That you see here outside is quite hot discussions. So it's completely fine for us. And in 2 days, we have approximately 20 presentations. So that's really a lot of submissions for these interesting symposiums. Now, before we start, let me just take several seconds to introduce our organizer. So first, I want to introduce Professor Chiara Bertolin. She is the full professor at Norwegian University of Science and Technologies in Norway, and her main expertise is in the non-destructive techniques for conditioning and monitoring. She did a lot of work in the climate risk assessment and also climate-induced degradation models by utilizing the machine learning activities. Also, our second organizer, Professor Chao, he is from Harbin Institute of Technology, which is one of the top engineering-focused university in China. He's also involved in the Shandong Provincial high-level talent program, and is the director of Marine Steel Structure branch of China Steel Construction Society. His research areas is in the polar structures, fatigue analysis, and also sea-based rocket launch by utilizing the machine learning techniques. Finally, I want to introduce myself. I'm associate professor at NTNU and also the chair of the ESI CTC19 technical committees. My main expertise is in the bioinspired designs and also deep learning networks. And I did a lot of networks by utilizing deep learning as core tools to investigate the mechanical problems and also to study the inverse designs of the high performance materials. I also built wider collaborations with the universities in the world and also industrial collaborations in Norway, and all these activities were supported by the national and the international funding agencies. So here is our short introductions of our mini symposiums. So now I want to introduce myself. The first speech is about our recent studies on the preliminary study on the prediction of mechanical behavior of hierarchical Voronoi-like mechanical mental materials via graph neural networks based approach. This work performed by my student Denis and also co-supervised by Chiara Bertolin and also Professor Andrea Tridello from the Politecnico di Torino. As we all know, hierarchical materials is quite popular in nature and across many scales. So starting from the centimeters to the millimeters and also to the nanometers, we all find these hierarchical designs. Currently, most of studies working on the regular hierarchical designs, and it has been extensively studied to demonstrate the great potential or great advantages by utilizing the hierarchical designs. Here, this is the work which utilizes the hierarchical designs to introduce or to control the Poisson's ratios from the positive to the negative in order to have better energy absorption capabilities. But as we all, that's observed that nature materials normally have the irregular hierarchical designs. Therefore, there is a gap or the knowledge gap between here. In order to solve these gaps, these preliminary studies, our goal is to solve that. Can we build hierarchical designs with finite irregularities and predict its mechanical behaviors? So let's look at these slides which show our methodology, how we perform it. So at the beginning, we start to generate the hierarchical designs with finite disorderness. Then simultaneously, we perform the finite element analysis in order to get the enough data to feed into the graph neural networks. In the meantime, we try to analyze these hierarchical designs with the disorderliness indices, which we defined is very important for the training or the design of the graph neural networks. After that, we design or customize the graph neural networks. Finally, we predict the mechanical behaviors of these that's complicated structures. So this is how we consider about these problems. Now let's look at the first step, how we generate irregular Bernoulli designs. So that means the first orders. The main steps include three. So first, we produce irregular Bernoulli cells by using random seed distributions, as you see here in the iteration zeros. Then we regularize these irregular designs by using Lloyd's algorithm progressively. After that, we evaluate the geometrical irregularities by calculating disorder indices we design. So on the right side, this is what I want to show you a representative, that's evolution of the iterations. Starting from the iterations equal to zeros to the iterations into 200. What we can visually observations is that at the final stage, the Bernoulli, diagrams becomes much more regular than the initial stage. So the method has already been demonstrated successfully to achieve it. The next question is that how we evaluate these financial disorderness. In here, what I want to show you is that the three indices we defined, to evaluate this disorderness. So H1 is the indices which evaluate the disorderness in the age of the cells. So for example, red ones has the 4H, black ones have the 7H. So this is the, the content of H1 evaluated. For the H2, it evaluated the parameter, diversities or the disorderness of the different, cells. And H3 is evaluate the area disorderness. So this H1, H3, H2, and 3, by looking at all these figures, after the iterations, 200 iterations, all indices, that has been largely reduced the disorderness. So this, that demonstrates our works, that our method actually works quantitatively, not only the qualitatively at the visual, observations. And these indices later would be very important for the graph neural networks, buildings. Now let's look at the next step is that now we want to generate irregular hierarchical designs. So similar to the first order, but here in the second order, we have to add the constraint of minimum distance to ensure uniform distributions of the seed points at second level. That's the additional steps we need to introduce when we play with the hierarchical designs. And in here, what you can see from the initial iterations equal to zeros and the iterations equal to 200. We could see obviously that the cells, not only the first order, but the second orders, they become more and more regular by utilizing the current method. So we also perform, let's say, the evaluations about the disorderliness. We always compare about the final step, j equal to the 200 iterations, to the initial, that's iterations, to see how difference. Therefore, the hollow rectangular bars represent the initial stage in the first order and the second orders, and the solid bars represent the final stage. Interestingly, for all, that's two orders, the disorderliness indices has been reduced. For three indices, especially for the first orders, the indices, that's reduced significantly. For the second orders, what we can see is that it decreased, but it does not decrease as much as the first orders. This could be understood is because for the second order, the topology would be constrained by the external cells. Therefore, for example, in the H1s, that it decreased only 6%. For the others, it's still decreased, but not decrease as the first orders to do it. That's that's the fundamental understandings to see the difference about these numbers. After that, we understand the geometries. Now we using the finite element analysis to perform the FE, that's modelings. So here we're using the abacus to perform the analysis, and material here we're using, assume very simple models, isotropic and homogeneous models. Constitutive law is just linear elastic, that models. Young's modulus was assumed 1 gigapascals, Poisson's ratio is 0.3. The element type using here is the plane string element. And looking at the right side, this is the motion details. We ensure that through the thickness of wings, at least the 4 element was, that's built in order to have the good accuracies of the result. And the left edge we fixed, and on the right edge, we applied compressions. Finally, we get the stress strain curves, and in order to post the process data, we extract the slope of these stress strain curves and obtain this effective steepness of, that's these curves. And we perform almost, let's say, 12,000 cases for future, that's deep learning studies. Now, looking at our graphs. So we utilized MATLAB 2024 to build our graph neural networks instead of, let's say, very popular PyTorch or the TensorFlow, because we want to customize everything by ourselves. And in here, the most important thing is that the mapping between the design and the graphs. So in here, all the nodes of the graphs represent the intersection points or joints in the Voronoi lattice. Edges represent the structure connection between the nodes. Edge features include the thickness of the structure connections, and the global feature encodes overall geometrical matrix. So in here, H3 was included for the total structure areas. So the target properties is the global stiffness, which we obtained from the finite element simulations. Now let's look at the method of the graph neural networks. For the left side, this is the general steps how we build the deep learnings. So we assemble data, load the data, and normalize it, build the training and build the data. And the training loops, I will introduce the details later. And we perform that validations, save the best point, and perform the final evaluations. In this training, that loops, here key point is that we use the 3 message passing layers in order to aggregate informations and transfer the informations. And the hidden dimensions of each layers is 64, and the nonlinear activation layers we use in ReLU layers for the simplicity, and the learning rate here we're using 0.01 for the optimizer atoms. Now we introduce everything about our methodologies. Therefore, we're looking at our results. First of all, this is the result about how the hierarchical Voronoi designs look like. First, look at the first rows. This is the first order. That results as the functions of the H2H1, H2H3. And the second rows is the second orders. What we can get the conclusion is that the diversities of our Voronoi designs is good enough course, for the H1s, it's span from the range from the 0.6 to the 1.8. And also, I mean that for the H2 is from the 0.1 to the 0.3. And here, what you can see here, H3 also have quite a large range from the 0.01 to the 0.05. In the second orders, the diversity is not as huge as the first order. The reason I have explained before is because we receive the constraints from the external, let's say, first order, I mean, that's H, in order to, I mean, that restricted the disorderliness, I mean, that's change. And of course, H3 it still can be, I mean, that's achieve quite a wide range, but H1, H2 is not as big as the first orders. After we visually, I mean, that understand the distributions, now we look at more deeper about the data distributions. So in here, this is the data distributions of the training data and also the testing data. Due to, I mean, that our method is to randomly choose the data from the total data. Therefore, the distributions of the training and also the testings, they are quite similar to each other's. If you look at the mean and the standard deviations, the numbers are very close. And looking at, and we also extract the 4 representative cases from the, I mean, that the training data and testing data by looking at the cases close to the minimum and the cases look at the maximums. What we can get the conclusion is that, yes, for the training and testing data, look at the minimum cases and the large case, maximum cases, the topologies shows the significant difference by consider about the minimum and the maximum cases. Okay, so we satisfied our, I mean, that's the results now of the generations. Now looking at the GNN predictions. So in here, this is the result to predict the non-dimensional, I mean, that's the stiffness, and the R squares is close to 0.8. So due to the high computational cost here, only 100 approaches has been performed in the preliminary studies. And we believe that if we increase the approaches, training more times, the prediction accuracies would be, I mean, that's increase much more. And also on the right side, this I would like to show you is the areas of the predictions and truths. And this non-dimensional areas is quite small, from 0.01 to the 0.01. So this is I mean, that's a quite, I mean, that's a good, I mean, that's indicators to show, I mean, that's the good predictions. Finally, I want to make my conclusions. So first of all, I mean, that we have successfully developed the methods to generate hierarchical, irregular Voronoi-like materials with finite disorderliness. So this is the important steps in here. Secondly, we are able to utilize the graph neural networks to predict the linear mechanical behavior of hierarchical irregular materials. Thanks a lot for your presentation, for your listenings, and welcome all the questions and remarks.